So today, we're going to start talking about things Lebesgue, and we'll start by drawing a proper O. Start by talking about the Lebesgue measure. Okay. All right. This is going to be by no means comprehensive introduction to the Lebesgue measure. It's going to be, kind of as quick and dirty as I can to get to the points that are essential and are essential for us. Skipping many proofs, some of them straightforward, some of them less straightforward. So if you want to learn about the Lebesgue integral, I suggest you go elsewhere to do that. This is just, kind of the rough cut. Okay. So what's the idea of measure? You can talk about measures on a set, and I'll introduce the definitions for doing that. And the idea is that a measure is a way of taking a subset of your set and talking about its measure. And so measure should be thought of as being somehow size, volume, something like that, okay? Now, we're going to be talking about a very specific measure, which is the Lebesgue measure. And the Lebesgue measure, is then going to be a measure on the set R, the set of real numbers. So therefore, what it will do is you give me a subset of R, and I'll tell you what its Lebesgue measure is. And there's lots of natural ways of sort of framing questions which lead to an answer, the Lebesgue measure. One of them is going to be for us a certain kind of object, which, a measure, which has the property that it agrees with our intuition about measure, in the sense that the measure of an interval will be the length of the interval. Okay, so it's going to be a concept of extending the notion of volume, size, length, however you want to think about it, from intervals to more general subsets of R. Okay, this I hope jives with some of the things that I said in previous lectures about the defects of the Riemann integral, where because you're approximating your hopefully integrable function by step functions, intervals there play a key role. And so as I said at that time, extending from intervals to more general subsets is a crucial part of defining an integral that's flexible enough for what we need. Okay, so first let's define the general concept of an outer measure. Now you can imagine lots of definitions for what a measure should be. What kinds of attributes of size, volume, length should you generalize in the notion of a measure? And we're going to sort of see two different flavors of measure. One's going to be an outer measure, and the other one will be a measure. And they come with different axioms. Okay, and we'll talk about a little bit about those when we introduce them. So first, we're going to just start with a set X. So sorry, there's a little piece of notation that I should introduce before we get started. And that's the extended real line. Okay. We're mainly going to be interested in the extended non-negative real line. Okay, and because the idea is when you have a measure, you want to allow the possibility of something to have infinite measures. So you need infinity there. And there's kind of an arithmetic that comes with these extended extended real objects. So any number plus infinity is infinity, any number plus minus infinity is minus infinity. There's a few conventions that you have to make a declaration about. One is that you declare that the operation of infinity plus minus infinity doesn't make sense, okay? And then the other is that you need to make a declaration about what 0 times infinity is. And the declaration you make is that that will be 0. Okay, so 0 times infinity is equal to 0 is the convention we go with. That's the convention you want to use in measure theory. There may be other places where you want to use a different convention. The point is, you get to decide this a little bit, because it's not like these are an actual field. So it's not a precise, a usual kind of algebraic object anyway. So there's some freedom in deciding how things work. Okay, so anyway, so an outer measure on a set X is a mapping. And I'll call it mu star. Okay, and so it's going to be a mapping like so. Okay, so 2 to the x here stands for the subsets of x. Okay, so that's my definition for the power set of x. Okay, or my notation for that. And so so an outer measure takes a subset and assigns to it a extended non-negative real. Okay, so again, possibly allowing infinity. Okay, so an outer measure should satisfy some properties. The outer measure of the empty set should be 0. If A and B are subsets of X that are nested like so, then the outer measure of the smaller one is smaller. Oops, that's not 3, that's 2. Okay. And finally, if you have a countable collection of sets, AJ, then we want to talk about the outer measure of their union. Okay. And what property should that have? Well, the requirement of an outer measure is that that's going to be less than or equal to the sum of the outer measures. Okay. All right. So I mean, these are certainly things you would expect any notion of measure to have. So this condition makes sense, right? So you want something that consists of nothing to have no measure. This is a monotonicity requirement, and again, this just any reasonable notion of measure should have this property. This one also seems reasonable. This is what's called countable subadditivity. Okay, so countable because I'm working with countable collections of sets, and subadditivity because of that. Okay. And again, this seems like a perfectly natural thing to require. And so then the question becomes, when you build, sort of a world using outer measure, does that world have nice properties? Okay. Okay, so let's just look at two simple examples. Well, one simple example and then the one we're interested in, which is less simple. Let's take just a set of all integers, let's say. Okay, then let's define mu star, which takes a subset of integers. So my 2 looks a little bit too much like a z for me. To the z. Let's take this to be what's called the counting measure. Okay, and so if you take a subset of integers, this is simply the cardinality. Okay, so this will be either some finite number if a is finite, or it'll be infinity if it's not. Okay, and so then you can verify pretty easily that it satisfies all of these conditions. Okay, all right. And then there's the case we're interested in, and we're going to define what's called the Lebesgue outer measure. Okay, and the way we do that, and so we're going to call it lambda star. Okay, so it's lambda star, taking 2 to the r to extended non-negative reals. And so we take a set A. Okay, and here's how we define its Lebesgue outer measure. Okay, so the first thing we do is we choose a collection of open intervals that covers A. Okay, a countable collection of open intervals that covers A. Okay, so A is going to be contained in the union of a bunch of open intervals, AJ, BJ. Okay, then for any such countable collection of open intervals, I'm going to take their sum, the sum of their lengths. Okay, so sum j equals 1 to infinity, bj minus aj. Okay. All right, so you give me a countable collection of open intervals that covers A, calculate their length. All right, then you take the inf of all such numbers. Okay, so the inf over all coverings of A by countable collections of open intervals. All right, so that's the Lebesgue outer measure. All right, so there's a couple of examples of outer measures. So it's very much not clear that the Lebesgue outer measure is an outer measure, but you can prove that it is. Okay, and I would say, I would describe the proof of that fact as direct, meaning you just go ahead and verify all these things using the definition. Okay, so so as an elementary example, to prove that the empty set has zero measure, you take any cover of the empty set. Well, everything covers the empty set. The empty set's going to be contained in any union. And so you just need to take for any epsilon, you need to find a union of intervals whose total length is less than epsilon. So you just choose them so they shrink quickly enough. Their lengths shrink quickly enough as you go off to infinity, and that'll do it. Okay. This seems like it's obvious, and indeed it is, right? You can just easily see directly from the definition that if A is contained in B, then you're going to have the monotonicity property of the Lebesgue outer measure, and this one is similarly not that difficult to prove, but it just requires getting in there and using the definitions with covers and stuff. Okay. All right. The thing that I most want to emphasize here, and I want to emphasize it because one, it's important, and two, it gives us a little bit of facility in playing with the Lebesgue measure, and that is, I'm going to prove the following thing: that if I is an interval then the Lebesgue outer measure of I is the length. Okay, and the length has the standard definition that if an interval is bounded, and so that means it's going to have endpoints at, let's say, A and B, then the length of the interval will be B minus A, and if it's unbounded, its length is infinity. Okay. So you kind of prove this case by case. And the first case you work out is the compact case. Okay. All right, so we need to show that this thing is equal to B minus A. All right, so first, let's let epsilon be some positive number. Okay, and here's what we're going to do. So we're going to take an open. So here's our compact interval AB, and we're going to take a certain open cover of AB. All right, and the open cover is going to consist of first one open set that covers AB. So we're already done covering. Okay, and I'm going to require this point here be A minus epsilon over 4, and this point here to be B plus epsilon over 4. Okay, so it overlaps it with a margin of error of epsilon over 2. All right, so there's one element of my open cover, and I need a bunch more, and I don't really care what these are because I've already met the covering condition, and so I just choose a bunch of other ones. And so let me kind of just draw them here. Okay, so I'm just going to choose a bunch of open intervals, throw them down anywhere you like. I'm going to draw them here like they're kind of nested, and the idea is that the lengths of these things are, the first one is going to be of lengths of epsilon over 4. The second one is going to be of length epsilon over 8. The third one of length epsilon over 16, and so on. So in general, it's going to be the length is going to be epsilon over 2j plus 1. Okay. Okay, so there's an open covering of the compact interval AB. Okay, so for this covering of AB by open intervals, the sum of the lengths of the intervals is, okay, so it's going to be the length of this one, which is b minus a plus epsilon over 2. All right. And then it's going to be sum j equals 1 to infinity epsilon over 2 to the j plus 1. Okay, and this sum is epsilon over 2. So I've configured the length of those intervals. All right. Okay, and so I know then that, so what I've done is I've found some open covering for which this number is equal to that. Okay, and so I know, therefore, that the since the Lebesgue outer measure is the infimum of all of these, it must be less than or equal to that number that I just found. Okay. Okay. And so since this is true for any epsilon, this shows that the Lebesgue outer measure of AB is less than or equal to epsilon. Okay, so sorry, B minus A. Okay. All right, so then I need to prove the opposite inequality. All right. And so then what I need to do is I need to show that if I take any open covering, okay, so I'm going to choose an arbitrary open covering, what I'm going to show is that the sum of these lengths should be at least B minus A. Okay. So now we're going to let A, J, B, J be a covering of the compact interval AB by open intervals, obviously. So by compactness, of AB. Okay, so I'm going to use the definition of compactness, or the version of compactness, which says that if I have a covering of my set by open subsets, then there's always going to be a finite number of these that will cover the set. Okay, so by compactness of AB, let J1 up to Jm be such that AB is covered by this finite collection of subsets. L equals 1 to M A J L B J L. Okay. All right, so then, okay. So then I have the sum from J equals 1 to infinity. Okay, so I want to look at the thing that I've been infing over here, which is the sum of these lengths. Okay, of Bj minus Aj is going to be greater than or equal to the sum L equals 1 to m of BJL minus AJL. Okay, just because these numbers are contained in these. Okay, and now, so now I'm going to use the fact that this is a finite collection of open intervals that covers AB. So the sum of the lengths of these must be at least B minus A, because if the sum of the lengths of these guys was less than B minus A, then they couldn't cover that, right? And this is going to be therefore greater than or equal to B minus A. All right. And so so this shows that for any covering of AB by open intervals, the sum of the length of those intervals must be at least B minus A. Okay, and so what that means is that B minus A is a lower bound for this collection of numbers. Okay. And so since the Lebesgue outer measure is the greatest lower bound, okay, then the Lebesgue outer measure must be greater than or equal to that lower bound that I just found. Okay, so thus B minus A is a lower bound for this set. Oh, sorry. Okay. And therefore, lambda star of AB is greater than or equal to B minus A, since lambda star of AB is the greatest lower bound. Okay. And so we've shown then that for a compact interval, its Lebesgue outer measure is its length. Okay, right, so that's kind of the hard case. The rest of them are easier. Okay, so the other cases for intervals follow from monotonicity Okay, so monotonicity of the outer measure is this property. Okay. From monotonicity of lambda star. Okay. So let's sketch how that goes. So if I is a bounded interval, then I, let's say that the closure of I is going to be A, B. Okay, so A may not, or sorry, I may not contain one or both of its endpoints, but certainly its closure will be equal to that. Okay, so then we can find compact intervals. Let's say C1, D1, and C2, D2, such that, okay, so the length of, let's say that, and so let me draw the picture here. Okay, so here's A, and here's B. Okay, and I'm going to choose, C1 to be a little bit bigger. And I'm going to choose C2, D2 to be a little bit smaller. Okay, and so the upshot of that is that D1 minus C1 is going to be equal to B minus A plus epsilon, and D2 minus C2 is going to be B minus A minus epsilon. Okay. And so the other thing that's going to be true is that lambda star of I, okay, because I is, so my interval I is has closure AB, so the interval I is contained in C1 D1. Okay, so that's going to be less than or equal to okay, so I already know, so this is going to be less than or equal to the Lebesgue outer measure of this, but I know that that is D1 minus C1 because I just showed for compact intervals, which is equal to that. Okay, so B minus A plus epsilon, and similarly by just going the other way around and using monotonicity in the other direction, I get lambda I is greater than or equal to B minus A minus epsilon, and then epsilon can be arbitrary. Okay, so that's that covers the bounded intervals. So if I is unbounded, okay, let M be any positive number. Okay, so unlike epsilon, M is large. And let A be some compact interval contained in I with B minus A greater than M. So then, again, we just use monotonicity. Lambda outer measure of I is greater than or equal to the outer lambda, the Lebesgue outer measure of AB. Okay, but I've already shown that the Lebesgue outer measure of the compact interval AB is B minus A, which is greater than or equal to M. Okay, and this must be true for any M, because you can always, for any M, you can find a compact interval of length larger than M contained in an unbounded interval I. Okay, and so therefore, the Lebesgue outer measure of an unbounded interval must be infinity. Okay. All right, so that proves this important fact that the Lebesgue outer measure generalizes the length of an interval. Okay. Let's look at an example of calculating the Lebesgue outer measure of something. Again, just using the definition. Okay. So let's take, so let's let C be a countable subset. So I claim that the Lebesgue outer measure of C is 0. Okay. All right. So let's see how that might work. Okay, so let's write C, let's label the points in C as xj. All right. All right, so what's the definition of Lebesgue outer measure? Well, again, there it is. Okay. So if I'm going to show that something has 0 measure, what I need to do is I need to show that this infimum is 0. So that means for any epsilon, I need to find an open covering of that set by a countable collection of open intervals, the sum of whose lengths is less than epsilon. Okay, now this little construction we did here gives us a clue already about how to do that, right? So all we're going to do is we're going to take the collection of points, and each point we're going to cover with an interval, and the length of those intervals is going to shrink just like that. Okay, so then let AJ, BJ equal, okay. So I need for the length of the interval around AJ, BJ to be epsilon over, according to what I observed here, I need the length of the interval to be epsilon over 2 to the j plus 1. And so the way you can achieve that, there's many, but here's one. You can go xj minus epsilon over 2 to the j plus 2, and then xj plus epsilon over 2 to the j plus 2. All right, so that guarantees that the length of the interval is 2 times this, which is epsilon over 2 to the j plus 1. Okay, so then, first of all, C is contained in the union of these. And the sum AJ, Okay, so again, I've jigged these intervals, so their length is epsilon over 2, which is less than epsilon. And so this implies that indeed, Lebesgue outer measure of C is less than epsilon for any epsilon, and therefore that must be equal to 0. Okay, and countable is the crucial thing there. Okay. And you can see how we've used countability of the set, okay, along with the construction of the Lebesgue measure to be to use countable collections of open intervals that cover the set to give a 0 measure of countable sets. Okay. So a countable set has measure 0. The converse is not true. And that is, there are uncountable sets with 0 measure. Let me give you an example of one such. And this is actually, an important set for a variety of reasons, none of which will matter to us too much in this course. Okay, and so what we're going to do is we're going to construct a bunch of subsets of the open interval 0, 1. Okay, the first set is going to be the open interval 0, 1. Let's call that C0. Then what I'm going to do is I'm going to remove the open middle third of that closed interval from 0 to 1. Okay, so I get two chunks like this. Okay, so C1, and you could do this in a variety of different ways, removing different proportions, but this is kind of a common construction, and this one ends up with what we want. Other rules for removing stuff at each step will not give you what we want here. Okay, and then you do this again. Okay, and removing from each of these their middle third. Like so. And so here, you're removing 1/9 from each of the intervals that remained after the first step. Okay, so this is C2, and so on. Okay, so you have this collection of sets, and the set that we're interested in is the set which we'll call C, and it's the set of points that remain after you do this construction infinitely many times. So the way you can define that is like so. Okay, and this is what's called the middle thirds Cantor set. Okay, so you have to do a bit of work to understand what goes on when you take this infinite intersection. What properties does this set C have? And I only really care here about two properties. What's the measure of C is 1, or the outer measure of C, and what's the cardinality of C? Okay, and so the fact is C is uncountable. In fact, the cardinality of C is the cardinality of 0, 1. Okay. And 2, that the Lebesgue outer measure of C is equal to 0. Okay. So C has many, many other properties, but that's not this course. All right. All right. So so there's an example of a set which is uncountable, but has 0 measure. Okay, so that's important to keep in mind, that just because a set has measure 0 does not allow you to enumerate it in a way like that. Okay. All right. Okay, so that's Lebesgue outer measure. Okay, so if the Lebesgue outer measure was sufficiently nice, we could kind of just walk away and be done with the Lebesgue outer measure. But the Lebesgue outer measure has an important deficiency. And the deficiency is represented by a certain property of the Lebesgue outer measure. Okay, and that is there exist a disjoint sets A and B for which the Lebesgue outer measure of the union is not equal to the Lebesgue outer measure, or the sum of the Lebesgue outer measures. Okay, so I know by countable subadditivity, I know that this is always true. Okay, and so what I'm saying, therefore, is that for these particular sets A and B, that inequality is strict. Okay. All right. And so it doesn't, and so because up here in the definition of the my axioms for an outer measure, right? I had nothing here about the disjointness of these sets, okay? And I just required this countable subadditivity here. And so the question that you want to know is, what if these sets are disjoint, okay? So AJ intersect AK is empty for every J and K, okay? Do you get equality here? Well, you know, the existence of a subset with this property says, no, you don't get equality there, okay? But you want equality, right? And so, you know, we kind of started our discussion, when we introduced the notion of measure, we thought about what are reasonable attributes of measure, and these are reasonable attributes of measure, but there are other reasonable attributes of measure as well. And, you know, the equality here of the measure of the union of two disjoint sets with some of the measures, that's a desirable property of a measure. And it's a property that the Lebesgue outer measure doesn't have, okay? So what one does is restrict the class of subsets. One measures. Okay, so the Lebesgue outer, or an outer measure in general, has the attribute that, and it's a nice attribute, that it can be applied to any subset of the set. Okay, so the Lebesgue outer measure makes sense for any subset of R. Okay, turns out that if we want this property, okay, then we must do one of two things. We must change the way we measure things, so change the definition of the Lebesgue outer measure, or restrict the kind of subsets we're working with so that we get equality here. Okay, and the way that you do that is you do the second thing. Okay, and there's deep sort of set theoretic reasons or motivations sort of underlying that dichotomy, and I'll chat just about the story behind what's going on there. Okay, so here's the and so all right, so we're going to now need to restrict to subsets of the power set. Okay, subsets of subsets. Okay, and so then you have to think about what are the attributes that such a collection of subsets should have. So you need to build a theory for doing that, and that's where we start talking about measures. And the first thing we do is we define the attributes of this class of subsets, and it's this. So the thing we're defining is what's called a sigma algebra. So this is a collection of subsets. So it's a collection, script A, of subsets. So this is a subset of the power set. And there should be some conditions that are satisfied by this. Okay, one is that the set itself, just the entire subset, should be in there. And so if A is in there, then so is its complement. And if AJ are in A, then so is their union. All right. So that's what a sigma algebra is. Okay, so as with any construction in mathematics, why are these the things that you require? All right. And the answer always at the end of the day is because it gives you a satisfactory theory that does what you want it to do. Because if it didn't do that, then it's just not the right definition. But that's somehow not a completely satisfying answer to the question. And so I think in a situation like this, it's maybe worth contrasting this definition with the definition of a topology. And so in your analysis course, so what's a topology? A topology is a collection of sets, and you declare those sets to be open. Okay, and what properties do open sets have? Well, in your analysis course, you learned that open sets had the property that if you take any collection of open sets, doesn't have to be countable like I had in my definition here. Any collection of open sets, their union is also open. Okay, and for open sets, it's not true, for example, that if you take arbitrary intersections of open sets that they're open, but finite intersections of open sets are open. Okay, so those are kind of the properties of open sets. Okay, a topology. And here it's different, right? So we're only working with countable collections of sets, and we require that countable unions remain in our collection of subsets, okay? And we have complements, okay? And that's not, the complementation doesn't hold for open sets, right? So the complement of an open set generally is not open. It's closed. It's always closed, but generally it's not also open. Okay, and I think a reasonable explanation for why you require countability here has to do with what you're trying to do with measures. And one of the things you're trying to do, again, is build a theory of integration. Okay. And one of the issues we noticed in our theory of the Riemann integral is its poor behavior with respect to sequences. And so the integrals that we're trying to build here will have good properties with respect to sequences. Sequences are, by their construction, countable. And so I think that provides some some kind of motivation for why accountability is important. All right, so let's think about some properties, and these are all sort of relatively elementary properties that you can prove that we won't prove. So I think the main thing that we're interested in here is the following. So actually, sorry, I'm really just gonna enumerate one property here. There's others you can, but there's only one I'm going to be interested in, and that's this: is that if and it's an analogous property to property 3. And then it's the property that not only are countable intersections preserved, but so are countable. Sorry, it's not only that countable unions are preserved, but also countable intersections. Okay. So that's actually quite easy to prove. If AJ is in there by property 2, you know that its complement is in there. Okay, and by property 3, you know that the union of those complements is in there. But the complement, a union of complements is by De Morgan's laws equal to the intersection, the complement of the intersection, and that gives it to you. So this follows from De Morgan. Oops. Okay. All right. All right, so that's what a sigma algebra is. All right. Now, there's a specific sigma algebra that arises from the construction of an outer measure. Okay. And this is just the first time you see this, there's just no reason to believe that any of this makes any sense. So, I'm going to make a bunch of constructions now that are not obvious. Okay. All right, so let's let mu star be an outer measure on set X. Okay. So a set A in X is what's called mu star measurable if for any set S in X, okay, so S is arbitrary, the outer measure of S, okay, is equal to the sum of the outer measure of the points in S that belong to A, plus the outer measure of the points in S that don't belong to A. Okay, and so you can see here that this is kind of getting at a situation like this, right? Because this set and this set are obviously disjoint, okay? And so what it's saying is that if you take a set S and you break it up into 2 bits, right, disjoint bits, right, one of the points in A and one of the points not in A, then you get an additive decomposition like this. Okay, and it's slightly unexpected that you know, you maybe would want A to be there, not S, but it is indeed S. Okay. All right. So the picture that I'll draw a picture to sort of represent this, and the picture makes you think that this should just always be true, and that therefore every set should be measurable. Okay, but that's just because my picture drawing skills aren't up to the task of representing sets that are not measurable. Okay, so here's my big set X, and here's S. Okay, and here's A. Okay, so I'm taking the points in S intersect A. Okay, and then I'm taking the points in S intersect not A. Okay, and I'm saying that the outer measure of S is equal to the sum of the outer measure of this bit, and then the sum of the outer measure of that bit. Okay. Okay, so that's the definition of mu star measurable. And the important fact here is that there exist subsets of R that are not lambda star measurable. Okay, it's, you know, not that hard to construct them. It's hard to understand, and there's some. It's not that hard to construct them, provided you think carefully enough about the set theoretic axioms that you adopt here. And there's a very bizarre, and I'll talk about this later on, bizarre circumstance that arises about non-measurable sets. Okay, but I'll get to that when I get to it. Okay, so there exist subsets of R that are not Lebesgue measurable. Okay. So we're going to call lambda star measurable. We're going to say that means we're going to call that Lebesgue measurable. Okay, so there exist subsets of R that are not Lebesgue measurable. Okay, all right. Here's another fact. And so this fact is a fact about the Lebesgue measure. The other fact is a general fact about outer measures. The set, or the collection, I'll say, of mu star measurable sets is a sigma algebra. Okay, so that is one of the reasons why sigma algebras are important, is that for any outer measure, okay, there arises this construction of a sigma algebra consisting of mu star measurable sets. Okay, and you know, this isn't that hard to prove. It's, you know, tedious and long, you know, because you have this sort of complicated property of measurable sets that you have to intersect with these attributes of an outer measure. Okay, so and then also with the attributes of a sigma algebra. Okay, so you know, there's a lot of bookkeeping to do there, but conceptually it's kind of a direct proof. Okay. Okay. So but for our purposes here, these are two facts that are not obvious, and I'm just asking you to swallow them. Okay. Okay, and so So now what we're going to do is we're going to take the outer measure, mu star, and we're going to restrict it to the sigma algebra of measurable sets. And what we get when we do that is we get a thing called a measure. Okay, so let A be a sigma algebra on X. Okay, so a measure on A. Okay, so now we're introducing the concept of a measure, not an outer measure. And so a measure is only going to measure elements of the sigma algebra script A. Okay, is a mapping mu such that okay, so I'm going to require that mu of the empty set be 0. Okay, and then I'm going to require sort of the right version of countable subadditivity. Okay, so here for an outer measure, okay, I required a property like this. Okay, but for measures, I'm going to improve that a little bit. For measures, I'm going to have if AJ are pairwise disjoint, okay, so that means any two of them don't intersect. Then the measure of the union is the equal to, not less than or equal to, but equal to the sum of the measures. Okay. All right, and so you see here that the properties of a measure, namely this equality here, are directly addressing the issue I had with the Lebesgue outer measure. Okay, and then the big fact again that I'm not going to prove is this: is that if so let's do it this way. So let mu star be an outer measure on a set X. And let's let script M be the set, or not to overuse the word set, be the collection of mu star measurable subsets. And let mu be mu star restricted to the measurable subsets. Okay, so I've already asserted without proof that this script M set is a sigma algebra, and what's also true is that mu is a measure. Okay. And so some terminology here. Okay, is that a set X with a sigma algebra is what's called a measurable space. Okay, and so the idea is that it's set up for you to use a measure, and X A mu is a measure space. Okay, so it's not only set up for you to use a measure, but you're actually prescribing one. There may be lots of them, but you're choosing one that gives you a measure space. Okay. All right. And so thus, where we've landed is that the set R. Oh, so sorry. Let me just before I do that. Okay, so more terminology. Now this terminology is general. Okay, now let me introduce some terminology specific to the Lebesgue measure. The Lebesgue measurable sets we're going to denote by L. And the Lebesgue measure is going to be lambda, completely consistent with the general definition. Okay, so the Lebesgue measure, the way you define the Lebesgue measure is no different from how you define the Lebesgue outer measure. Okay, so the Lebesgue measure of a set is still that. Okay, the only difference is you're now restricting the kinds of sets A that you're measuring. Okay. Okay, and so where we've arrived at is we have a measure space. Okay. And a measure space is a thing which you can use to define a theory of integration. Okay, and that's what we're going to do next time. But I want to maybe round out the discussion of Lebesgue measure by talking about a little bit about the existence of non-measurable sets. Okay. So as I said, the actual construction of a non-measurable set isn't hard. It's certainly hard to visualize, and so I can't draw it, for example. And it turns out the construction, and so I'm just going to chat my way through something here. I'm not going to write anything down. Okay, so the construction of this example of a non-Lebesgue measurable set uses fundamentally in its construction what's known as the axiom of choice. And the axiom of choice says, so it's an axiom for set theory, and it says if you give me a collection of sets, okay, arbitrary collection of sets, that there's a choice law, and the choice law is a rule for choosing from each of those collection of sets that you gave me a single element. Okay, so that's the axiom of choice, and it's an axiom of set theory. So there is a way to do this. So this is, on one hand, seems non-controversial because the existence of a choice function like that seems like something you should take for granted. The problem, or depending on your point of view, a problem with the axiom of choice is that it's not a constructive choice function, right? So it's arbitrary, and so this can lead you to constructions in mathematics which you can't really say anything about. They're not constructive, okay? And so there's a whole subset of mathematics which is called constructive mathematics, which is sort of dealing with the axiom of choice, well, basically by seeing how far you can get without having to use the axiom of choice. And measure theory, or Lebesgue measure specifically, is a place where the axiom of choice plays an absolutely pivotal role. And so what I want to do is describe for you that story. And so, as I say, the existence of subsets that are not Lebesgue measurable relies on the axiom of choice, okay? And so you might want to try building the whole edifice of Lebesgue measure in a way that doesn't rely on the axiom of choice. And you can do that. So, you need to sort of dig back into the foundations, but you can build a theory of, the real numbers, and which doesn't rely on the axiom of choice. And that in that world where the axiom of choice is not one of the axioms of set theory that you allow, in that world, every subset is Lebesgue measurable. Okay, and that's nice on the one hand, but it also inhibits you from doing certain things that that you would rather be able to do. Okay, so leaving off the axiom of choice seems like it's the right thing to do, but it just turns out that it's kind of not. All right, and so this was something that people devoted a lot of time to thinking about. And two people who thought about that were mathematicians and logicians, Banach, who we've already talked about with respect to Banach spaces, and Tarski. And they generated a paradox around the axiom of choice, which is connected to Lebesgue measure, okay? And the paradox is this, is that if you build a set theory which relies on the axiom of choice, okay, then you end up with these non-Lebesgue measurable sets, okay? And then what they proved was that you can do the following construction. You can take the unit ball in R3, okay, so just the set of points in R3 of distance less than or equal to 1 from 0, okay? And if you're assuming the axiom of choice, you can cut up this ball in R3 into a finite collection of subsets, okay? And you can rearrange these subsets. And what I mean by rearrange is you can move them around in such a way by just translations and rotations. And so, translations and rotations ought not to change the volume of the subsets or their measure. And then rearrange them in such a way that they form 2 unit balls, okay? And so this seems very counterintuitive, right? So you take a ball which has some volume, okay? You chop it up into a finite number of subsets. And so as far as I'm aware, the latest, the lower bound on the number of subsets is 5. So you chop it up into 5 disjoint subsets, and then you can reassemble those into 2 unit balls. Okay, so that seems just wrong. Seems like you should not be able to do that. Well, the issue is that the subsets that those 5 subsets, they're not just things you could take by taking an orange and a knife and cutting up into 5 separate bits. And so your intuition about the ridiculousness of this isn't quite accurate. The subsets are extremely complicated. They're not Lebesgue measurable. Banach and Tarski sort of presented this paradox as a reason for not, or at least as an argument for not abiding by the axiom of choice, because the axiom of choice leads to this absurdity. Okay. Well, the fact is that in modern mathematics, what most working mathematicians have done is they haven't sort of looked at the Banach-Tarski paradox and said, oh no, I need to reject the axiom of choice. The axiom of choice just has too many good things that come with it. Instead, I'm going to accept the axiom of choice, and along with it, I'm going to accept the craziness of non-measurable subsets of R, okay? And so the point of that little discussion is that there's a world where all subsets are Lebesgue measurable, okay? But that world comes at a cost, and the cost is rejecting the axiom of choice. But as I say, most working mathematicians do not reject the axiom of choice. They just accept the axiom of choice and accept that there's certain things that come along with the axiom of choice that are counterintuitive. And the counterintuitiveness is hardly surprising because, these choice functions, we don't know very much about them. And so it's possible that these choice functions will lead you to choices that behave in ways that you're not necessarily happy with, but you accept that because the axiom of choice has lots of good properties, or sort of leads to lots of constructions in mathematics that are useful. And just sort of as an instance of those properties is back in when we talked about vector spaces and the dimension of a vector space and bases for vector spaces, I made the statement that every vector space possesses a basis, okay? That statement actually is equivalent to the axiom of choice. Okay, so it's not just that the axiom of choice allows you to make that statement. The statement that every vector space possesses a basis, that statement is equivalent to the axiom of choice. If you sort of, filter through the foundations or the axioms of set theory. And so, if you throw away the axiom of choice, you're also going to have to throw away the very useful fact that every vector space has a basis. Okay, so that's an example of the kind of thing that the rejection of the axiom of choice forces you to do without. And as I say, most working mathematicians live with the axiom of choice. Okay, good. So that's Lebesgue measure. Next time, we're going to use the Lebesgue measure to talk about the Lebesgue integral. But that's next time.